as quick as I can, but I do have quite a few slides to show you. So if you're late and you miss your train or plane, sorry about that in advance. Today I'm gonna talk to you about GPU drivers and not those big black cats that you find in a jungle usually. So in retrospect, I think we did a good job at choosing the name because dealing with GPU sometimes feels like fighting a wild animal. But yeah. So who am I? Boris BREZILLON, working at Collabora. I think I've been working on Mali GPU drivers for the past 5 years or so. Doing both the kernel side driver and the user side driver. I initiated the Panthor effort, which is the driver for new Mali GPUs. And also initiated the Vulkan driver effort on the use-based side of things. Nowadays, it's mostly others contributing to those drivers, but I keep reviewing and adding a few features when I have time. And yeah, I've been contributing to those drivers for a few years now. As everything's graphic, if you want to start doing something, it usually starts with drawing a triangle. So I'm gonna start with that and give you a quick recap of what this is that GPU do and how they do that. So most of the time you start with a set of vertices. You give a few transform matrix on top of that. You pass that to what we call the geometry pipeline. So that's something you have to pass somehow to the GPU. And you pass other arguments that you need to render things differently. So it's basically all about configuring the graphics pipeline. Out of the geometry stage, you get geometry shapes. Most of the time, those are triangles. They can be more complex than that, but the basic shape is just a triangle. I've never got to draw anything but a triangle. I leave that to others. I just take care of the driver side of things. Once you have prepared those shapes and projected them on the screen space, you want to fill them with colors. And that's what's done in the rasterizer stage. Again, that's mostly about configuring the GPU pipeline. So again, that's parameters you give to the GPU at some point. And how do you apply colors? Most of the time, you take those colors from what we call textures, which is basically a square image, and you provide a point to sample the color from such an image. And yeah, you end up with a triangle in the end. But let's have a look at what's those different concepts. And they actually map to some very simple concepts that I'm sure as kernel developers, you like to know what those things map to. And when it's mapping to something very simple, that's even better. So when you look at all those things, they actually, most of them map to buffers. Vertices, they go in vertex buffers. Pipeline configuration, everything goes into what we call a command strip buffer. Those are describing commands that instruct the GPU to reconfigure the GPU pipeline. Texture buffer. And the buffer where you store the final image that you're going to display on the screen, that's called the frame buffer. So basically everything is a buffer there. There are other aspects that you should care about when you do GPU stuff. As you can imagine, GPUs are fast. They are faster and faster every year, just like CPUs are. They tend to be a bit slower than GPUs in general, but the fact that there are so many processing units in there makes it so that they can do things very fast because they parallelize the work. So each side is pretty damn fast. But the problem is when you have to actually synchronize between the CPU and the GPU. And sure, this is not so slow. when you have to do that, but compared to how fast each component is independently, it starts to matter if you just wait every time you ask the GPU to do something, that it finishes what you ask him to do. The other problem is that, yeah, drawing a triangle is fine and it's pretty simple, but most of the time when you, I don't know, when you have a game engine, it's not just a single pass that you need to render things. You have to render everything that's static in the scene. Then you have to render characters. Then you have to render lighting, and so on and so forth. So, yeah, basically when you render things, it takes multiple iterations until you reach the point where you have the whole scene rendered. So again, if you have to wait between each pass for the previous one to be finished and the CPU has to then submit the next one, it's going to take a long time. And that we don't want. And yeah, I mean, the CPU has also other things to do in the game engine. If you think about physics, if you think about AI for anything that's not every characters that you have in the scene or whatever. So yeah, clearly the CPU can't wait on the GPU to finish what it has to do. So what we need to have here is a way to submit jobs and then let the GPU do itself and then be signaled when it's done doing what it has to do. So you need to submit and then check if it's done or if it's not done. So most of you know subsystem, where the subsystem deal with most of the hardware complexity kernel side. And that's not really true for graphics driver. Actually, those drivers are split between a user space driver and a kernel space driver. And that is for a very simple reason. When you look at what a GPU driver does, there's so many complexes that you really don't want it to happen in kernel space where there is elevated privileges. So I'm talking about shader compilation. That means you have to have basically a full compiler that does compile the shader at runtime. So that's pretty big and likely to have security issues that you really don't want to pull kernel side. Pipeline configuration, you can't imagine how many parameters you have to tweak to get what you want rendered correctly. So yeah, putting all that in the kernel mod driver is not really an option. And what the kernel driver does is really minimal compared to what the overall driver, so the combination of user mod driver and kernel mod driver does. Basically what it does is it manages memory for you. It deals with, or it provides ways to synchronize stuff, so being able to know when a GPU job is done and when a GPU job has to wait on some other job to be done before executing and that sort of stuff. And it also bridges between the user mod driver and the actual hardware. So that would be receiving interrupts or, I don't know, programming registers when you have to, even though nowadays it mostly goes all through the command stream. So yeah, it's mostly about interrupts, let's say. So yeah, when you look at what each part does, you can say, oh, that's pretty even. But when you look at the code repartition, it's actually not even. I mean, when you look at Mesa, which is the stack of user space drivers for GPUs, and you just look at one specific driver and compare it to the size of the kernel mod driver that exists for this user mod driver, it's incredible how much code there is in user space compared to the kernel space. So, yeah. Of course, user space can't do everything on its own, but most of it is still done in user space. Yeah, that's basically what I said. There's a few things that the user mod drivers have to deal with. The list is not long, but it's quite complicated. On the other hand, the kernel mod driver, it doesn't do much, but it has to do it well. I listed a few things. Memory management is key here. Synchronization is key. We can't get away with that. Then you can add things on top to spice it up a little. Power management, you want suspend resume to work correctly, especially if you're running on an embedded device. Frequency scaling, that's the same thing. You don't want your GPU to run full power all the time. And all sort of debugging features on top that you want to add, like perf counters, I don't know, coordinates or that sort of stuff. But yeah, I mean, that's not much, but the kernel driver needs to do it well. So let's have a look at the first item I listed, memory management. As for the CPU, if we want to do things seriously, we need some isolation, and that's what an MMU provides. So you, thanks to the MMU, each GPU context can be isolated from its neighbor, and also you can easily map memory without having to deal with memory fragmentation and all that sort of stuff. I won't detail how those MMUs work. I mean, it's pretty much the same way it works for CPUs. So I would defer you to the talk that Lorenzo gave on Monday, for instance, or I mean, there are plenty of other materials online that you can check and see what this is that an MMU does and how it does it. What I want to look at is what we do with that MMU and how we expose that to the useMod driver. So there's actually two models. The one that we were using 3 years ago or so, and the one that the new drivers that were merged since then are going for. The whole model is the virtual address space is entirely controlled by the kernel. So every time you allocate the buffer, you also get a virtual address for this buffer in the GPU space. And that works fine for APIs like GL, because everything is opaque there. You just allocate the buffer, and you don't have to deal with where it is in GPU address space. It's just transparent for you, and when you want to execute some job, you also pass those buffers around, so the kernel driver knows where things are, and it can tell, it can do the pipe and whatever. But for new APIs, that's no longer the case. If you look at Vulkan, for instance, you need to have fine-grained control from the useMod driver on where this is that the buffer will be mapped in the GPU space. And that's also true for compute APIs like CL or others. So we clearly need a change of model there, and the new model is actually delegating everything that is to do with address space management to user space. So the user space has to create a VM context explicitly, and it's then responsible for assigning virtual addresses to buffer objects. So that's one part. The second part I mentioned earlier was synchronization. And it's actually all based on some core component that exists in the kernel driver that's named DMA fence. And the DMA fence itself it's nothing. It's just an interface that someone has to implement. And this interface, it exposes a state, which is signaled or unsignaled. By default, the fence starts in an unsignaled state, and at some point, something signals the state. And basically, for GPU job, that would be when the GPU is done doing what we ask him to do, and then it will signal the fence from the kernel driver. Also attached to this fence is the context. The way GPUs work is that they are having hardware queues where you can push a lot of jobs, but then they are executed asynchronously. So there's a deep pipeline there, and we need to know where in this pipeline the scheduler inside the kernel is. And so that's what the sequence number is about, being able to figure out where things are currently and that sort of stuff. So each fence will be assigned a unique sequence number, and usually it increments one by one over time. So now let's look at the actual implementation of this interface. There are hardware-backed fences. That is basically every GPU driver has one. So it usually relies on some hardware concept that reflects the fact that the job is done. It can be a piece of memory that's shared between the CPU and the GPU, and then when the value changes, then that means the fence is signaled. Or it can be interrupts, and then when the CPU receives the interrupts, it has to check some register, whatever. It doesn't matter how it's implemented. The only thing that matters is that the implementation has to reflect when the fence is signaled by changing the state of the fence. There's also container fences, so you can have software concepts on top of an hardware fence. For instance, we have the fence array, which collects a bunch of fences, and then it only reflects the signal state once all the underlying fences are signaled as well. Pretty much the same thing with fence chain, except it's not an array, it's a single link list, but it's pretty much the same approach there. And there are also purely software fences. The step fence is just a fence that either always signaled or unsignaled. It doesn't change in state. And the scat fence is just a proxy. So yeah. This fence, the MF fence object, it's actually all kernel internal. So when you are from user space, you don't see those. They are only used for inter-driver synchronization. But there are ways to express the state of the fence to user space. And that's what we call fence containers that expose DMA fences to user space. So we have basically two of them. DRM seek_obj, which is specific to the DRM subsystem, so the subsystem that deals with GPU. And there's also the sync file that can be used for any subsystem that would want to participate in the synchronization that we mentioned earlier. So yeah, it's basically just an object that reflects the state and reflects the state to the space. And you have IO tools to query the state and the sorts of stuff. And the last one that I want to talk about is the one that we use for implicit synchronization. Remember when I said that in GL everything is opaque and you don't get to control where a buffer is in memory? That's pretty much the same thing for synchronization. So in GL, you don't get to know when a job accesses a specific buffer object. It's all internal to the kernel driver. And so we are using the DMA-USV synchronization primitive for that. And basically what our DMA-USV is an array of fences that each driver will add to the RESV every time it manipulates a buffer object. And so every time it manipulates a buffer object, it says, okay, I'm going to read this buffer. And so the next one that wants to write to this buffer, it has to wait for me to finish. And it's basically just a queue of components that are going to access the fence. Except it's not directly visible to user space. It's all implicit. So yeah, you can when you add a fence to this object, you can say, I want to add a read fence because I'm going to read the resource, or I'm going to write the resource. So you can select which kind of access you want to do. And that's basically the big picture of synchronization that we need to have in GPU drivers. So now let's have a look at how we use these synchronization primitives. There is the old word and the new word. I mentioned that GL is all about implicit synchronization, and that's basically how it works. So when you pass a job to the kernel driver, you also pass all the buffers that are going to be accessed by this job. And you also say, I'm going to read or write each of them. Then the kernel driver extracts those dependencies, and it adds them to the list of dependencies that is attached to the job. And when the job is queued, it also creates a fence and adds its own fence to the buffer object, so that the next one that wants to access this buffer also has to wait for the new job that's targeting it. So that's implicit synchronization. There was also a bit of explicit synchronization. So most drivers allow you to also get a fence back, or get a fence back through a sync object or a sync file. So you could still wait for some job to land, but you couldn't really define which explicit job you wanted to wait on. It was all implicit. In the new world, this is all explicit. So by default, we don't wait on any implicit fences that are attached to buffers. That means that the user mode drivers has to figure it out on itself. It has to extract the kernel mode driver. It does extract the fences that are attached to the reservation object still, but when it does that, it actually check if those needs to be waited on or not. And by default, there's nothing that needs to be waited on there. On the output side of things, the kernel mode driver now can return multiple, or can fill up multiple sync objects. And by default, it won't participate in implicit synchronization. It will still add its job fence to the resv objects, but it will do so with a specific flag that says, I'm there, I'm going to do something with the buffer, but it's the user space driver that's going to decide whether it's a read or a write. And so it's the user space driver that's in charge of reconciling the implicit synchronization word with the explicit one. So that's basically how job submission works in practice. When you get a job submit, most of the time you can receive multiple jobs because you want to avoid the overhead of going back and forth between kernel land and user space. But let's just have a look at a single job first. The first thing you do is check that every parameter that are attached to the job are valid. That is, all the things that make the job usable by GPU, but also all the synchronization that are attached to the job. So input synchronization, and also the object that you are supposed to update with your own demystify at some point. So that's the first thing. The second thing is, at some point you decide that everything is correct in the submission, and it says, okay, I'm gonna initialize my job, and after that point you can't fail. Because once you start exposing your DMA fence, there's a rule that says that a DMA fence has to be signaled infinite time. And once you start exposing that to some external components that can be a buffer resv, or that can be a DRM sync object, whatever, it has to be a signal infinite time. So you can't fail after that point. You have to succeed. So you have to make sure that in the first step we've seen there, everything is correct. Because after that point, you're not allowed to fail. And you have to make sure that everything will execute correctly. I mean, the GPU can still crash, but otherwise, if you forget about crashes, forget about GPU crashes, everything should work. That means that there should be no allocation after that point. It should all succeed. And yeah, once you've done that, you basically just push the job to the scheduler, and you're done. You got new fences attached to your sync objects, and at some point later, you're gonna call sync object wait and check the state of the fence. Huh? Simple. I mean, this dance is quite crazy in practice, and every time I have to remember what this is that's needed to have something that complicated. And yeah, I think the main key point you have to remember is that the fencing, DMA fence rules are very strict. And one of these rules is that once you've exposed the fence to someone, you have to guarantee that it will be signaled. You can't fail in between. So that's good. We've seen the two main components that are needed for a GPU driver to function correctly. Now let's have a look at what's there and the kernel mod driver, because I mean we are all kernel developers, so I guess you care more about the kernel mod driver than the user mod driver. So that's pretty obvious what you'll find there. There's a new API front end that takes the IOCTLs and turn them into something. And behind that, there's three main components. The buffer object management layer is here to allocate free buffers, make sure that they are backed by actual physical pages and whatever that is related to memory management. There's the VM management, which is kind of related to memory management too, except this is really dedicated to everything that has to do with the MMU, so where you map this buffer object in GPU space. And the last thing is the scheduler, so everything that has to do with synchronization, making sure that when you get a job, it waits for all its dependencies before it gets passed to the hardware. Make sure that when a job is done, the fence that attached to the job is signaled so it can unblock others that are waiting on it. And yeah, each of these components actually map to hardware components. For VM management, it's the MMU. For buffer object management, is either the system RAM if you are in the UMA architecture, or the virtual RAM if you are on a discrete GPU with its own memory. And for the scheduler, nowadays there is actually firmware schedulers in place, which means most of the complexity is now deferred to firmware. That wasn't the case, at least on older Mali GPUs, but the ones that they released, like it was 5 years ago or so, they do have firmwares in there that do part of the scheduling. So far, so good. The internal of the driver is pretty complex, but the U API is relatively simple. You basically have several IOCTLs, and each are related to each of these components we've seen. Buffer object management, you can create or destroy a buffer object. That would be BO create. And then there is a common IOCTL that's valid for all drivers, which is called gem close. That's pretty obvious what they do. They just deal with the allocation and then return a handle that describes this object. BOM map offset is just a trick that we have to use because when you want to CPU map a buffer and it goes through some file descriptor that's not an actual file, you have to give an offset to a map. And so this offset is not a real offset. There's no real file there, but we just have to give a fake offset and say, okay, this buffer object will be accessible through this offset when you map it using the render node FD. VM management, VM create, VM destroy, the names are pretty obvious, nothing complicated there. VM bind, that's a single IOCTL for both mapping and unmapping. And in some cases, the mapping and unmapping requests can be asynchronous. Still the same problem. You don't want to wait for GPU jobs to run, so what you will do is say, okay, I want to map this buffer object once this job is done, or I want to unmap this buffer object once this job is done. So you will pass synchronization primitives to the job, and VM bind will take care of queuing that and then doing the unmapping or mapping at some point later. And because there is this asynchronicity that exists, you also need a way to query the state of the VM, just in case something fails during the asynchronous map or unmap. And then there is the job submission side of things. So you need to have a way to create and destroy a context, a scheduling context. That would be, in Panthor, that would be Panthor create, group create, destroy. And then you need a way to submit GPU jobs. So in Panthor, that would be group submit. And what each job contains is very specific to each driver. So in case of Panthor, you will pass command stream buffers to the job. You will pass all the dependencies that the job has to wait on, and also pass all the sync objects that you want to be updated with the job fence. And also there's some very common query IOCTLs that basically query any kind of device properties there. There's nothing fancy. It's just about exposing what the hardware is capable of, and it's again very hardware specific. So yeah, there's actually quite a lot of things to do. The UAPI is relatively simple, but the internals, they are not so simple. So DRM actually provides you with a way of with a set of libraries to help you with all the work that needs to be done for each of them. For buffer object management, that would be DRM gem something. That again, depending on where your RAM is, it would be a different component. So that you can only decide based on what the GPU is using as memory. It can be video RAM, it can be system RAM, whatever. For VM management, it's common to everyone. It's called DM GPU VM. It basically manages an interval tree, and it keeps track of mappings that exist. So you can merge the mappings and destroy the mappings and whatever that needs to be done with VM management. I mean, it's not so different from what they do in the memory subsystem. And I was actually surprised to see that I'm not the only one to face problems with memory reclaim. And yeah, the last one is the job scheduler. So that one would be using DRM GPU scheduler, which is a generic scheduler for everything that has to do with GPU jobs. So buffer management in practice, you pick the component that's matching the type of RAM you're using. You have a bunch of functions to implement. These are all the gem object functions interface. Most of them have a default implementation. So unless you know really that you don't want to use the default implementation, you should rely on the default one. Then you should provide your own create object function, which is your constructor of the object that you, of the driver specific object that you want to expose. And then all the IOCTLs we've seen so far, they are just wrappers around those functions. Gem close is already there, so you don't have to implement anything. VM management, again, those are just wrappers around the GPU VM interface. So you have to implement a few things because mapping and unmapping is very hardware specific. You have to know the format of the page table. You have to know how to flush the TLB and that sort of stuff. But other than that, the whole interval tree management and the mappings and whatever, this is all generic. And for the scheduling, again, you can use GPU scheduler. It will take care of dependencies, weights. It will take care of signaling the fence. And it will just pass the job when it's ready to execute to the driver. So you have to implement a couple functions, but other than that, it's all handled in the core scheduler code. Job submission, I don't think I need to go over it into too much details. We've seen it with the sequence diagram I showed earlier. But for each and every step I described, there is a specific either DRM GPU VM function or DRM sched function. So for each of them, you'll have helpers that help you deal with what's most complicated there. I draw a big red line there, and it's the point where you're not allowed to fail in the submission process. So you have to make sure that every allocation is done before that. You have to make sure that everything is correct in the job definition before that, because after that point, you just can't fail. You have to succeed with the job submission. I mean, if the GPU crashes in between, if the job is not fully executed, that's fine. But you can't block the system if others are waiting on your business to make progress. Yeah, that's great. You've learned a few bits about GPUs and GPU drivers, but why should you care? I mean, when you look at the ecosystem, most vendors have their drivers now. I think the last one was Imagination, and the driver landed 2 years ago or last year, I don't remember. So yeah, why do I need to be involved in that? Well, the thing is, if you take Panthor, for instance, we have the bare minimum to have things working, but there are still quite a few features that are not there. And that, I mean, if you're volunteering for implementing one of them, I'd be more than happy. And also because, I don't know, people like to learn new things, so why not learn about GPU drivers? But there's also something that came up a few times at Kernel Recipes this year. And yeah, I mean, you've heard that at least 2 new drivers are targeting Rust as a language, and the VM subsystem, that's one more after Apple. And one of them is for Mali GPUs, so it's supposed to replace Panthor. And yeah, if anyone is fluent in Rust and wants to learn about DRM, we're accepting contributions, and we're more than happy to see you contribute to your tier. Yeah, that was it. Thanks a lot.
Hey, I have 2 quick questions. So back for implicit synchronization, when you have implicit synchronization using GL, for example, do the submits have to block, or?
No,
yeah.
So implicit synchronization is not synchronicity. It's just that you don't have to pass the synchronization objects around. You just pass the buffers, and then the system extracts the dependencies from the buffers. So you don't have to say, okay, I'm going to wait on this fence. You don't have to keep track of all the fences attached to the job that you submitted previously.
I see. And the second question is, can you briefly re-explain what bookkeep is for fences?
Yeah, that one is, yeah, I realized I was not super clear. So bookkeep is about letting the user mod driver decide when it's actually accessing the buffer. Because you've seen that with the new model, we now have, we no longer pass buffer objects around saying, okay, I'm going to access this buffer object. So basically, when you have a job that's targeting a specific VM context, it means that any buffer object inside this VM might be accessed. But in practice, there's only a few of them that will be accessed. So we're just leaving an opportunity to the user mod driver to say, okay, potentially, I'm going to access everything. But in reality, the user mod driver knows that, okay, I'm just going to access this one and this one. So there's no point saying that, okay, I'm going to read or write every buffer that exists in the VM. The user mod driver gets to decide, I'm going to read that one, and so I'm going to upgrade this bookkeep fence into a read fence or a write fence. But most of the time, the user mod driver won't update all the buffer objects as read or write. They will just update a few of them.
So every single buffer object in the VM gets bookkeep, and then eventually only the ones you're touching get read or write.
Yeah, yeah.
All right, thanks.
question? Guess you're all free then.
No, just wait the concluding word from a hand, but yeah, thank you.